Hello there, welcome to Ethio-Hahu tutorial. I'm Getachew and today we are going to see about thermodynamic processes. In the previous classes, we have seen about thermodynamics and first law of thermodynamics. Thermodynamics is the study that's concerned with the concepts of heat and temperature, and first law of thermodynamics, which is the law of conservation of energy. Energy is transferred in thermodynamics in the form of work done by the system or work done on the system, and in the form of heat added to the system or extracted from the system. And we have also seen about internal energy of an ideal gas. The internal energy of an ideal gas is directly proportional to the temperature of the ideal gas. These are the concepts that we have seen in the previous videos. Today we are going to see about different types of thermodynamic processes, such as isothermal process, a process of constant temperature, isochoric process or isovolumetric process, a process of constant volume, isobaric process, a process of constant pressure, and adiabatic process, a process in which no heat is added to the system or extracted from the system. The first process is isothermal process. What does it mean by isothermal process? Isothermal process is a process of constant temperature. A process that takes place at constant temperature is known as isothermal process. From chemistry, we know Boyle's law. Boyle's law states that the pressure of an ideal gas is inversely proportional to volume. That means the pressure of an ideal gas is inversely proportional to volume. This implies pressure times volume is equal to constant. As the volume of the gas increases, the pressure decreases and vice versa. From ideal gas law, we know that PV is equal to N times RT, where N is number of moles, R is universal gas constant, T is absolute temperature, P is pressure, and V volume. Having seen this, let's draw pressure versus volume graph for isothermal process. The horizontal axis is volume axis and the vertical axis is pressure axis, as we have seen in Boyle's law and ideal gas law. In ideal gas law, temperature is constant, R is constant, number of moles is constant, therefore PV is equal to constant. The pressure is inversely proportional to volume, in this case as well as in this case. When we draw pressure versus volume graph, the pressure decreases as volume increases. As we have seen in this graph, when there is an increase in volume, the pressure gets smaller and smaller. And when the volume decreases, the pressure gets higher and higher. When the volume is V1, the pressure is P1. And when the volume is V2, the pressure is P2. Therefore, as the volume increases from V1 to V2, the pressure decreases from P1 to P2. Therefore, this is a pressure versus volume graph of isothermal process. Let's write first law of thermodynamics for isothermal process. First law of thermodynamics is written as change in internal energy is equal to delta Q minus delta W. In this case, we have seen sign convention. Change in internal energy is positive when there is temperature rise and negative when there is temperature drop. Delta Q is positive when we add heat to the system and negative when we extract heat from the system. Delta W is positive when work is done by the system and negative when work is done on the system. Having that sign convention, change in internal energy is equal to delta Q minus delta W. For isothermal process, the temperature is constant. Since the temperature is constant, the change in internal energy is zero, because for ideal gas, last time we have seen about internal energy. For example, for N moles of an ideal gas, internal energy is the same as translational kinetic energy in case of monatomic ideal gas. This is equal to 3 over 2 N times R times T. When T is constant, internal energy is constant. If T is equal to constant, change in T is equal to 0. This implies change in internal energy is equal to 0, because these are constants the only parameter that internal energy depends on is temperature. As the temperature of the system or the gas becomes constant, internal energy is constant, and the change in internal energy is zero in an isothermal process. Therefore, first law of thermodynamics is simply delta Q is equal to delta W. Work done in an isothermal process is equal to delta Q, because this is zero. This minus delta W comes to the left. Delta W in an isothermal process is equal to delta Q. When we add heat to the system, delta Q is positive, and work done in an isothermal process is positive. When we extract heat from the system, delta Q is negative, and work done in an isothermal process is negative. Since the pressure is not constant, how can we find work done in an isothermal process? Because as we have seen so far, this volume, this is pressure. Pressure versus volume graph looks like this one. When the volume is V1, the pressure is P1. And when the volume is V2, the pressure is P2. Therefore, in this case, the pressure is not constant. Work done is equal to P times change in V is used only if P is equal to constant. Otherwise, if the pressure is not constant, we cannot use this simple definition. Rather, we need to find the area under this curve. How can we find this area? That's the point. Consider the previous pressure versus volume graph for isothermal process. When V is V1, P is P1, and when V is V2, P is P2. Now, consider this change in V, infinitesimal volume change in V. For this infinitesimal change in volume, the pressure P, and this pressure P is constant for this infinitesimal change in volume. For small change in V, P is assumed to be constant. Therefore, work done is equal to simply P times change in V. That is the area under this rectangular strip. The area of this rectangular strip is equal to base times height. Our base is delta V and our height is P. P times change in V is work done. This is W star. This W star is the amount of work done to change the volume of the gas by change in V. Between V1 and V2, we have infinite number of rectangular strips. If we sum up all these areas, we get total work done. Work done in an isothermal process is equal to the sum of this work done, delta W star. This delta W star is the area of this rectangular strip. When we sum up all the area of these rectangular strips, we get total area of this. And this is equal to the sum of area A asterisk. This area A asterisk. To find this total area, we need to apply integration. If change in V is very small, we can convert this change in V into derivative. Therefore, work done in an isothermal process is equal to the integral P times dV from V1 to V2, because A asterisk is P times delta V. The equation of this graph is P is inversely proportional to volume, and PV is equal to constant, say K, and P is equal to K over V. This is the equation of this graph. Therefore, this is equal to the integral from V1 to V2 times P is K over V times dV. And this is equal to the integral from V1 to V2 of K is constant. We can pull it out from the integration, dV by V. And this is equal to K times the integral of dV by V is ln of V, limit of integration from V1 to V2. This is equal to K times this integration ln of V2 minus ln of V1 from properties of logarithm. Ln of V2 minus V1 is simply k times ln of V2 over V1. This is work done in an isothermal process. But what is K? From Boyle's law, PV is equal to constant, means P1 V1 is equal to P2 V2, and this is equal to K. Therefore, work done in an isothermal process is equal to, simply in place of K, P1 V1 ln of V2 over V1, or simply N times R times T ln of V2 over V1, because from ideal gas law, PV is equal to N times RT. Since T is constant, PV is equal to nRT is constant. Therefore, work done in an isothermal process is given by P1 V1 ln of V2 over V1, or nRT ln of V2 over V1. Let's come to isochoric process. Isochoric process is a process of constant volume. If there is no change in volume, no work is done by the system or no work is done on the system. There is no expansion work or compression work. In this case, delta V is 0, because V is constant, means delta V is 0. Since delta V is 0, delta W is equal to P times delta V is also 0. Therefore, first law of thermodynamics for this process is delta U is equal to simply delta Q, because the change in internal energy is equal to delta Q minus delta W. Since V is constant, change in V is 0, no work is done on the system or by the system, this goes to 0. Therefore, delta U is equal to simply delta Q. This is first law of thermodynamics for isochoric process or isovolumetric process. The third process is isobaric process. Isobaric process is a process of constant pressure. Work done in an isobaric process is simply delta W is equal to P times delta V, because since the pressure is constant, we can use simple definition for work done, P times delta V. From mechanics, work done by constant force is simply F dot delta S. This definition is all holds true only if this force is constant or average force. Otherwise, if this force is variable force, then this work done is not defined by this expression. Rather, we use graphical analysis to find work done. Likewise, if the pressure is constant, we can use for work P times delta V, and if pressure is not constant, we cannot use this definition. Rather, we can use the area under PV graph, like an isothermal process. Therefore, delta W is equal to P times delta V, and first law of thermodynamics for this process looks like this one. Delta U is equal to delta Q minus P times delta V. This is first law of thermodynamics for isobaric process. The fourth process is adiabatic process. Adiabatic process is a process in which no heat is added to the system or extracted from the system. Heat is not added to any system or extracted from the system, and such a process is said to be adiabatic process. Delta Q is 0 in this case. Since delta Q is 0, first law of thermodynamics, delta U is equal to minus delta W, because delta U is equal to delta Q minus delta W. Since delta Q is 0, delta U is equal to minus delta W. This is first law of thermodynamics for adiabatic process. Therefore, we need to know first law of thermodynamics for different thermodynamic processes. Having seen this, let's do examples. The first example, an ideal monatomic gas expands Here, monatomic ideal gas. Last time we have seen about monatomic and diatomic ideal gases. Therefore, an ideal monatomic gas expands isothermally from volume 0.5 cubic meter to 1.25 cubic meter at a constant temperature of 675 Kelvin. If the initial pressure is 1 times 10 to the power of 5 Pascal, find A, the work done on the gas, B, the thermal energy transfer delta Q, and C, the change in internal energy. To do this, let's have given V1 is 0.5 cubic meter and V2, the final volume is 1.25 cubic meter at a constant temperature of 675. T is equal to 675 Kelvin. If the initial pressure is, if P1 is equal to 1 times 10 to the power of 5 Pascal, find A. Delta W in an isothermal process is equal to simply P1 V1 ln of V2 over V1. This implies delta W in an isothermal process is equal to P1 is 10 to the power of 5 Pascal times V1 is 0.5 ln of V2 is 1.25 over V1 is 0.5. Since they have same units, the unit cancels and this is equal to 0.5 times 10 to the power of 5 is 5 times 10 to the power of 4 times ln of 1.25 divided by 0.5, and this is equal to 45,814.5 Joule. This is work done in an isothermal process. B, the thermal energy transfer, delta Q. To find delta Q, we need to apply first law of thermodynamics. Since delta U is equal to delta Q minus delta W in an isothermal process, the change in internal energy is 0 in this case, because since the temperature is constant, the change in internal energy is 0. Therefore, this is 0, and hence delta Q is equal to, when we bring this to this side, it becomes positive, delta W isothermal. From sign convention, if work is done by the system or expansion work, delta W is positive. Therefore, we use as it is, positive 45,814.5 Joule. This is the amount of heat added to the system. C, change in internal energy, which is equal to 0. The second example, an ideal gas expands adiabatically to 3 times its original volume. In doing so, the gas does 720 Joule of work. A, how much heat flows from the gas? B, what is the change in internal energy of the gas? And C, does its temperature rise or fall? To do this, first let's have given, let V1 is equal to V and V2 is equal to 3 times V1, which is equal to 3 times V. And this is expansion work. Therefore, delta W is 720 Joule. Since it is expansion work, work is done by the system. From sign convention, this is positive. Therefore, how much heat flows from the gas? It says A, delta Q is 0 because the process is adiabatic process. That's why delta Q is 0. B, what is the change in internal energy of the gas? The change in internal energy of the gas is equal to delta Q minus delta W from first law of thermodynamics. Since delta Q is 0, this is 0. Delta U is equal to minus delta W. From sign convention, delta W is positive, and this is equal to minus, in place of delta W, 720 joule. This is delta U. And the negative sign shows that there is a decrease in internal energy. If there is a decrease in internal energy, the temperature gets smaller and smaller. Therefore, C, does its temperature rise or fall? Its temperature falls, because since change in internal energy is negative, there is temperature drop, because internal energy is directly proportional to temperature. When there is a decrease in internal energy, there is a decrease in temperature. As an exercise, an ideal monatomic gas contracts in an isobaric process from 1.25 cubic meter to 0.5 cubic meter at a constant pressure of 1.5 times 10 to the power 5 Pascal. If the initial temperature is 425 Kelvin, find A, the work done on the gas, B, the change in internal energy, C, the energy transfer delta Q, and D, the final temperature. This is all about today. Next time, we'll see another topic. Until then, have a nice time.